This is today's topic: performance, understanding performance. So I hope you guys can hear me and see the screen. Can you confirm that? Can someone say?
Yes, sir, we can hear.
Okay. Well, right. So performance is a theme that runs through this course, not just this course, but in the courses that you will be following after this. So in a computer system, performance apply at various different levels, at various scales. So you know the composition of a computer system. Now you have idea, right? From transistors and silicon substrate up to software, application software, and algorithms, right? So throughout all these levels, performance, the concept of performance applies, and we'll be talking about it throughout this course as well as the courses that you will be following afterwards. So at the algorithm level, we talk about performance. Simply saying, at the algorithm level, the algorithm decides the number of operations that you need to execute to get something done, right? For example, say you're solving a problem about sorting a list of numbers, a simple problem like that. So to solve the sorting problem, you have different solutions, right? You have different algorithms, merge sort and selection sort, bubble sort, whatnot, right? You know there are different algorithms that you can use to solve that problem. So based on the algorithm, the number of operations that you need to do is determined, right? So if you take bubble sort, the number of operation, number of SOPs that you might need to perform is different from if you're performing merge sort, if you're using merge sort to solve the same problem. So at that level, at that high level, based on the algorithm that you're using to solve your problem, the number of operations that the computer needs to perform is going to change. So that is related to the time complexity of the algorithm as well. I think you have some idea about the notion of time complexity already. So yeah, so at that level, that is how performance is coming into the picture. Then when you go to the next level, where the systems level, where we talk about an instruction set architecture, a programming language that you use to convert your algorithm into source code, and then a compiler tool chain, which allows you to translate your source code into a machine code, right? So at that level, at the systems level, the notion of performance boils down to the number of machine instructions executed per operation, right? So say if you are talking about a SOP operation that you use to swap two elements in an array, based on the programming language, based on the compiler tool chain, based on the instruction set architecture, the number of machine instructions or assembly instructions that you will need to perform the swap operation can change, right? Based on what sort of constructs the programming language allow, what sort of statements, what sort of operations the programming language allows, and what sort of instructions we have in the instruction set architecture, atomic instructions, and then how the compiler uses those atomic instructions to compose a list of assembly instructions for the same program, same software program. All these things affect the end result, which is the number of machine instructions executed to get that operation done, right? So at the system level, we are going into a smaller granularity rather than compared to the algorithm. So then if we go even inside, even deeper, the hardware level, the processor microarchitecture level, and then the related subsystems like memory. At that level, we talk about how fast can these instructions be executed by the actual hardware, right? So we have a list of instructions given by your compiler, assembler, and whatnot. And how fast can these instructions be executed? Physically, how fast these can be executed is how we look at performance at that hardware level, right? So that at that level, we have to, these abstractions of microarchitecture, memory, and so on, the functional units, they are built on logic gates and then in turn on transistors and so on, right? So the properties of all of these sub-elements come into the picture when we talk about performance at the hardware level. So of course, then there are some other associated things at the system level, like input output and operating system services. So at that level, we talk about how fast these IO operations can be executed. So this is actually, this includes hardware level things as well as system level things, right? System level performance as well as hardware level performance we have to talk about when we talk about these peripheral elements in our computer system like input output controllers and operating system. So when we talk about the performance of a computer system, we have to talk about all of these things and we have to understand how the performance at these different levels, different places are connected to each other. So before we go and talk about how to evaluate performance or how to assess performance, we have to answer this question. Why do we need to know about performance? What is the purpose? What is the purpose of knowing performance in a computer system? So one obvious answer is when you are given a computer system, to analyze the performance of that system, analyze that system and measure the performance and report it and summarize it to compare with other computer systems or to figure out whether this system, the computer system that you're looking at, is good enough for a certain problem, right? We build it as engineers, we build systems to solve problems. So whether a given system you are looking at is good enough to solve a problem, or maybe like whether it is too good, whether it is more than good enough, so maybe you are wasting resources, things like that, right? In engineering context, to understand the appropriateness of the system, we need to understand the concept of performance related to that system. And also to make intelligent choices when selecting a system to solve a problem or when designing and building a system. When designing and building a computer system, you will have to make choices. What are the functional units I'm going to use? How am I going to connect? What is the overall operation in this system, right? A lot of design choices are there. So to make intelligent choices as an engineer, you need to understand performance of the computer system and of its components at different levels and different scales. So then as an engineer as well as a consumer, you need to understand performance to see through the hypes that are used in marketing. Remember that overclocking example we talked the other day, where manufacturers, when they face this power wall, they would increase the clock frequency further. They use that marketing gimmick to get better sales. So to understand the actual situation behind these marketing gimmicks and hypes, you need to understand how a system works properly, works correctly, and understand how performance actually derives from its implementation. So maybe perhaps most importantly out of all these reasons, understanding performance is very key in understanding the underlying organizational motivation. When you are learning how a computer is designed, or when you yourself is going to design a computer system, understanding the motivations behind certain design decisions, certain organizational decisions, you need to know how performance is related to that, right? Why is a microarchitecture implemented in a pipelined manner, right? Why is it done that way in nearly all the CPUs that we have in the world today? So you need to understand how performance is related to that particular design choice, and you will do that in this course. So that is perhaps one of the most important things for you as a student in computer engineering, to understand why we design computer systems in certain ways, right? So why some hardware is better than others for different programs, right? For a given particular computer program, a software, why is it good to use a certain hardware, certain processor system compared to some other type of a processor system, right? So choices like that. What factors of system performance are hardware related? Certain factors of performance. Now we know that performance is applied or discussed at different levels, at different scales, and they are connected, right? So which factors of the performance are related to the actual hardware, which are related to the software? So you would need to know that. So unless you know that, you can't go and figure out how to improve performance by using software solutions, by using hardware solutions, right? So to solve such problems in computer systems, you need to understand performance. So as designers of computer systems, you need to understand all of this related to performance. And of course, how does the machine's instruction set affect performance? I hope you get the idea of why you need to understand the concept of performance before we go and talk about how performance is related at all these different levels. Right. Now, when we talk about performance, we need to define what we mean by performance, right? Performance is a very vague term. We need to give a definition to it based on the context. Our context is computer systems. Okay. So let's take a different example, different context. Say we are trying to define performance here for passenger airplanes. Right, we have 4 different passenger airplanes, a couple of Boeing models, Concorde and a Douglas DC-850, right? So here, the measure, the definition that we are trying to apply for performance is passenger capacity, right? Some models can support who can carry a lot of passengers, while some other models can carry only a small number of passengers. Then for the same candidates, we can consider a different definition for performance. This one, second one is cruising range, the number of miles a particular plane can go, the maximum number of miles it can go in a single flight, right? So you can see this Douglas DC-50 has a long range compared to the others. While the capacity, when it comes to capacity, the same plane, the capacity is quite small compared to the others. So then we have another definition, cruising speed. The speed of these different airplanes, right? So here the Concorde is the obvious winner. It can go quite fast compared to the other ones. So we have these different definitions, right? So what do you think? How can we pick a proper definition for this particular context? Defining performance for an airplane. What do you guys think? Which one is better? What do you feel? Can you give me an answer?
Having some sort of a weighted mean for each pass.
Having some sort of a weighted mean, weighted average for each of these definitions. So that's an interesting idea, right? So combining these definitions to come up with an overall one where, say, you put a weight for each of these definitions, which is an interesting suggestion. So the basic concept behind that answer is these different definitions are useful for different situations, right? Based on what we are interested in getting out of this system. So if our interest is in the capacity entirely about how many passengers that we can transport in one go, in one flight, if that is the only concern, then passenger capacity is a good enough definition for performance. But then say, if our concern is about going the longest distance in one flight without thinking about how many people we can fit into the plane, how fast we can go, or how quickly we can go, right? If those things are not concerns, then cruising range is good enough definition. So it depends. The proper definition for performance depends on what we need from the system. So, like you said, for a general scenario, maybe a combination of all these might be a better answer. For example, here in this fourth definition, we are using passengers into cruising speed. So if our concern is about getting as many people as possible to a destination as quickly as possible, then such a definition, passengers into speed, might be a better definition. And if the range also comes into the picture, we can come up with another sort of an equation or another combined measure to define performance. So the idea is it depends, the measure, the definition depends on our requirement, what we expect from our system. So in computer systems, we are interested in getting lot of computational work as done as quickly as possible, right? So very generally saying that is a requirement. If we take specific problems, there may be specific requirements like correctness of the answers produced by the computer, different things like that. The security, like whether we can provide a guarantee that third parties can't access our data, right? Things like that comes into specific problems. Very generally saying, what we usually want from a computer is to perform computation as quickly as possible. So with that in mind, we define two things. We come up with two definitions for performance, which are again related to each other. The first one is response time. Response time is how long it takes to complete a task, how long it takes to complete a program, right? Task here again, slightly vague term. Task could be a program, task could be part of a program like a SOP operation, let's say, or task could be an instruction itself, right? So response time can apply at, it's a definition of performance that we can apply at different levels in different scales. So however it is, it's a measure about how quickly we can do, basically how long, how much time does it take to complete a task, right? Simple enough. Then the other definition we use in computer systems is throughput. Throughput is the reciprocal of response time, or like 1 over response time. How much work can we do per unit time? How much work can a computer system do per unit time? So again, work is slightly vague. Work could be programs or operations or instructions, right? At different levels, we can define work in different ways. So how many instructions can we complete per second is a way to apply or look at performance using this definition, throughput, right? And of course, they are related to each other, response time and throughput. Let me ask you this question: how are these two definitions, measures, response time and throughput of a computer system affected if we do one of these things? Let's first take the first question: replacing the processor with a faster version. Okay, so we have a computer system, we keep everything constant, we only replace the processor with a faster version. Same processor, but a faster version. Using a faster clock speed, let's say, right? The same program we are running, everything else is the same operating system, but not everything else is the same. We are only using a faster clock rate. How is it going to affect the response time, and how is it going to affect throughput? Can someone say? Can someone say? How do you think?
So I guess replacing the processor with a faster version would reduce the response time, while adding more processors would increase the throughput.
Okay, so let's take one by one. Replacing the processor with a faster version would reduce the response time. Okay, so that is understandable and that is acceptable, right? Can everyone agree with that, or is there anyone who does not agree with it? With the faster version of the processor, the time it takes to complete a task, whatever the task may be, would likely reduce, right? That is the whole idea of using a faster clock. So yeah, we can expect if we use a faster processor, faster clock rate, then the response time should reduce. Then what would happen to the throughput? In the same scenario, using a faster clock rate, faster processor, response time would reduce. So we could expect the throughput to increase, right? The amount of work we can get done per unit time should increase because these two are related, response time and throughput. Okay, so that is, I think, straightforward. Then the second one is adding more processors. So Aditya said we can expect the throughput to be increased by adding more processors, which is a reasonable answer. But we need some more information here, right, to answer that question.
Yes, I assume a task is done individually in one processor.
Yes, exactly. We need some more information, which is basically whether there are tasks or things in our program which can be done individually on these extra processors at the same time, right? If that is the case, if that is the situation, then of course we can expect the throughput to increase, right? Because for, say, instead of just a single processor, now we are talking about 2, 3, or 4 processors doing work in parallel. So completing the work faster overall. That is, instead of completing one task per second, now we are talking about 2, 3, or 4 tasks completed per second. A very rough answer. But that the underlying assumption is there are enough work in the program or in our task that the processors can actually do in parallel. But that is always not the case in computer programs. Remember last time we said, if we want to use these multiple processors, utilize multiple processors very effectively, we need to explicitly write our programs in that way, right? To be able to be run on parallel processors. So yeah, so this needs additional, the second question needs additional information. But with that assumption, we can assume that the response time, if all the processes are same and if all the work or tasks are same, the response time would probably be same, but the throughput might increase if we can do these tasks in parallel. Right, so very good. Okay, so for now, we'll focus on response time in this discussion, right? Throughput, of course, we will talk about, especially in the middle of the course where we talk about computer organization and concepts like pipelining and so on. But for now, we'll stick with response time. Okay, now we are trying to come up with some simple definitions for performance here, right? So we'll define performance here, saying 1 no execution time. Execution time is a version of response time, right? How long it takes to execute or complete a task. So we can define performance as 1 over time, right? The shorter the time, the better the performance. Okay, so what we mean by relative performance is just a way to compare two systems using this definition of performance, right? Using the response time definition of performance, how to compare two systems. For example, we have two systems, X and Y. X is, when we say X is n times faster than Y, what we mean by that is performance O of X, performance of system X, or performance of system Y is equal to N. Or in other words, according to this definition, the response time of system Y or the response time of system X is equal to N. Right? Very simple stuff. So, an example, time taken to run a program. We have two systems A and B. We try to run the same program on these two systems. When we run the program on system A, it takes 10 seconds. On system B, it takes 15 seconds, right? So execution time of on system B or execution time on system A is 15 over 10 is 1.5, which means system A is 1.5 faster than system B, right? Very simple stuff. So measuring execution time. When it comes to measuring this execution time or response time, especially at the system level, right? When we have a computer system, we want to measure its performance using our definition, response time or execution time. Both are the same thing. One way we can do it is using elapsed time. Elapsed time is the total time taken for a task to be completed on this system, including all aspects, everything, including processing, including time taken by the I/O input subsystem, time taken by the memory subsystem, time taken by the operating system. Operating system is another set of programs, right? And of course, there may be some idle time inside that elapsed time as well. Why? Say, now, in a general purpose computer system, you have so many programs, so many tasks running at the same time. But in reality, they are not all run at the same time. You run one program for a small time, then give the processor, stop that program and give the processor to a different program, right? The processor switches between these programs, different programs. So you have hundreds and hundreds of programs running on your computer. Not all of them are running at the same time, right? And even say operating system is the program, and other application programs need to ask operating system to do certain things, right? Like say write to the disk, write something to the disk. Operating system can only do that. The application programs can't directly write to the disk. So operating system, the certain program in the operating system have to be run, certain function in the operating system, which we call as system calls, have to be run by the application program. So those programs will take time, and sometimes programs need to wait until some other programs complete. So there will be idle times as well when we take elapsed time for a certain task, right? When you run a program, all of these elements will be there in that total elapsed time. So this is good to determine the performance of the system, the overall performance of the system, right? That is the perceived performance by the end user. But for the designer, for engineers like you, CPU time is a different measure that you would need to define the time spent processing a given job or a given task, right? The time spent related to the given task. So some of these additional things are not included when we talk about CPU time. So we discount things like how much time the IO system took, right? For example, how much time did the network controller take to send a piece of data, send a packet of data over the network. So your CPU might have had to wait until the network subsystem, network controller tells the CPU, okay, I completed the job, you can go ahead now. So such times are discounted when we talk about CPU time and other the time taken by other processes, other programs, right? Because the operating system gives the processor to a certain program, then stop that program and give the processor to another program, right? Likewise, that is how these threads are scheduled in a CPU. So all those things are discounted. All the other extra non-related things, when we, the things that are non-related to the particular job, particular task that we're talking about are discounted when we talk about CPU time. So things that are included are operating system overheads that's related to your program, right? Your program might ask the operating system to write something to the disk. So that time is related to your program. Even though the operating system does it for you, that time is related to the program. So those things are included. Things like the idle times and some certain idle times, time taken by other jobs while you wait, right? IU some systems can give big ways, right? For example, if you're designing an embedded system and you're waiting for an input which is coming from outside, that wait time is not part of the CPU time of your system, of your program. Okay, so yeah, so this comprises the user CPU time and system CPU time. Everything related to your application, your program, but other stuff are discounted from there. Yeah, so different programs are affected differently by CPU and system performance based on what these different programs do, right? What are the hardware these different programs use? What are the external communications that these different programs do? So how elapsed time and CPU time is defined for different programs. So how, when you measure elapsed time and CPU time, the differences between them, between the programs are based on those reasons, right? For one program, elapsed time might be a lot bigger than CPU time, while for a different program, elapsed time and CPU time might be closer to each other. So yeah, those are the two ways that we measure performance. Right. Now, when it comes to the hardware level, we talk about clocking, right? When we talk about synchronous digital logic circuits, we talk about clocking. I'm sure you guys are familiar with this from the concept. You're familiar with from digital design. So the idea is we use a signal which goes from low to high and high to low periodically, right? In set times. We use such a signal to synchronize the operations of our logic hardware, right? At the rising edge, your circuits are designed to do certain things, and at the falling edges, your circuits are designed to do certain things, right? So these things might periodically happen, or it might happen alternating in alternating ways, but synchronized to these edges in the clock. So when it comes to talking about performance at hardware level, the response time is quite related to this measure clock period, right? The time for the clock to go from, say, complete a single cycle, go from low to high, high to low, and then again go from low to high. So, right. Very simple example. Period is the duration of clock cycle, and say we can say the clock period is 250 picoseconds, so 0.25 nanoseconds, right? Then the same thing can be said using the reciprocal of this, which is clock frequency, the rate. How many cycles does the clock have or clock go through per second, right? So the same thing can be said. The clock is 4 gigahertz or 4,000 megahertz. The clock has 4 billion cycles per second. So I'm sure you guys are familiar with this concept, so we'll not spend too much time on it. By the way, I'm hoping to take a little bit more time than the allocated lecture time today. So I think the mechatronics students are having a lecture right after this one. So just feel free to go to that lecture. I will upload this recording to the Moodle page, so you can check out the last little bit that you might miss later on. But if you don't have anything, feel free to stick around and take part in the discussion. So yeah, CPU time, we can define very simply as the number of clock cycles into the time taken by a single clock cycle, right? So the total time taken by the CPU is how many clock cycles the CPU went through, and into multiplied by the time taken by a single clock cycle. Very simple stuff. So we can write the same thing in a different way using clock rate instead of clock cycle time, right? Rate is basically 1 hour clock cycle time. Right. So when we use the CPU time measure to define performance, performance can be improved by, based on this equation, by reducing the number of clock cycles, right? If you reduce the number of clock cycles, the CPU time should reduce according to this, right? Number of clock cycles reduced, then the total CPU time should reduce. Basically, performance should improve. Or else, the other way to do it is increasing the clock rate or reducing the clock cycle time, reducing the clock period, right? So if we increase the clock rate or reduce the clock cycle time, then again the CPU time should reduce, meaning the performance should be improved. But the catch is these things are not entirely independent. These things are not mutually exclusive, right? If you try to reduce the number of clock cycles, there's a good chance that the clock rate would increase. Or if you try to, clock rate would reduce. If you try to increase the clock rate of your system, then there's a good chance that the number of clock cycles would also have to increase. So these things are linked. There are connections between them based on the actual hardware. So as a hardware designer, you would often have to trade off these two elements. Clock cycle, clock rate. For example, if you're designing CPU and you want to say reduce the number of clock cycles taken by the CPU by a certain operation, for a certain operation. So when you want to reduce the number of CPU clock cycles, that means you need to get more work done in a clock cycle, right? In a single cycle, you need to get a lot more work done. That is the idea, right? You have a certain amount of work to get done, and it takes current hardware takes a certain number of CPU clock cycles. So in a cycle, you get a certain amount of work done. So if you want to reduce the number of cycles your CPU is taking, that means you have to make the hardware a little bit more complicated to get more work done in a single clock cycle. You need to add more hardware, make a complicated circuit. So when you do that, that is going to affect the cycle time. More complicated the hardware is, the bigger the cycle time is going to be. Why? Because the time for the outputs to stabilize and settle at the end of this complicated circuit is going to be longer, right? So your clock cycle also has to get longer according to that. So you would have to come up with some sort of a trade-off. As a designer, you need to understand whether adding more complicated circuit into the system is going to pay off at the end of the day, looking at the increase in cycle time as well, right? So likewise, you would need to look at both of these factors and come up with a good trade-off, a good balanced point where you would get the maximum performance out of the system. But you can't just look at these elements individually and come up with design decisions. Right. So here's an example. The program runs on computer A with a 2 gigahertz clock, and it takes 10 seconds. Right? We have a program, we have computer A. For that program, computer A takes 10 seconds, and the clock used is 2 gigahertz. Now, what clock rate must a computer B use, the second computer use, to run this program in 6 seconds? Right? Now you want to design the second computer with a different clock rate to complete the same program in 6 seconds. Unfortunately, to accomplish this, computer B will require 1.2 times as many clock cycles as computer A to run the program. Right? So you are going to design a different system to run the same program faster, but based on how you design this second computer B, that is going to take more clock cycles compared to computer A for the same program. Right? 1.2 times as many clock cycles as computer A takes. So what is the answer here? What is the clock rate for computer B to complete this program in 6 seconds? Can you guys work it out and tell me the answer? Yeah. So here's the summary. The same information organized in a better way. Computer A uses 2 gigahertz clocks, 10 seconds CPU time. You are designing computer B. The target is to complete the same program in 6 seconds. You can use a faster clock, but using the faster clock, meaning you are going to use more clock cycles, because to use a faster clock, your hardware needs to be made simpler, so you can't complete the same operations the same way. Okay, so Ridma and Adip are saying 4 gigahertz. Is that right? Did the others get the same answer as well? Yeah, so you can work it out, right? Clock rate of B is clock cycles for system B or GPU time, which is 1.2 times the clock cycles in computer A over 6 seconds. That is the target. So the clock cycles in A is GPU time for A times clock rate. Same equation, right? That we had earlier, simple equation. So 10 seconds into 2 gigahertz, meaning 20 billion clock cycles. So go back to our original equation here, 1.2 times 20 billion divided by 6 comes up to 4 gigahertz. So your answers are correct, right? So simple math. Okay, here's another exercise. We are looking at the same set of instructions, same sequence of instructions are being executed on two CPUs, A and B. A turns out to be faster than B. What could be the reason? We have the same program, same assembly program, right? Same set of instructions executed on two CPUs, A and B. So we can assume that A and B are built using the same instruction set. A is faster than B. It can complete the program faster than B. What could be the reason? We don't know the exact reason, but could each of these be a reason? For, let's say the first one, A is having a complex circuit. A is having a complex circuit. Could that be a reason for A to be faster? Is it possible? Can you tell me? A having a complicated circuit, could it be a reason for A to be faster? Adipa says yes. Adipa, can you reason your answer out? Why could it be a reason?
Of course, complex means some sort of improved technology. So, of course, the reduced clock cycle time, therefore, lesser time to execute the same program.
Yeah.
If we can say complex circuit and the frequency is higher, then we can say yes, right, sir?
Yes, yes, very good points by both of you. So it boils down to this thing, right? So we have a complicated circuit. Complicated circuit would mean the number of cycles could be less, right? We could, because we have complicated hardware, we could do a lot more work in a single cycle, right? That could be a reason for the system to perform faster. But that is also going to affect the cycle time as well, right? Cycle time is also going to increase because our circuit is more complicated. But at the end of the day, it's going to be a combination of both of these, right? So that if the time you save by reducing the number of clock cycles is a bigger factor compared to the time increased by having a slower clock cycle or smaller, a longer clock cycle, then of course you would end up with a better performance, right? Overall faster time. So yes, A can be a reason. A having a complicated circuit can be a reason that A performs faster, right? We cannot say that it is the reason. Of course, there's not enough information here, but it is potentially possible that A's complex circuitry is a reason that A is performing faster. But we need to look at both the number of cycles as well as the cycle time to come up with a solid answer for this to actually see whether this is true. So yes, very good. So the second one is the clock frequency of B is less than A. Clock frequency of B is less than A. The clock frequency used for system B is less than A. So A has a higher clock frequency, B has a lower clock frequency. Could that be a reason why A is performing faster? Again, yes, right? It could be a reason. A having a faster clock would probably mean A's circuitry is simpler compared to B. So it is possible that A uses more clock cycles to complete the same amount of work, same instructions compared to B, compared to system B. But again, if the time saved by having a faster clock is a bigger factor than the time increased by having a larger circuit, then of course it is possible that the clock frequency of B is less than A, being a reason for A being faster, right? So, okay, the clock frequency of B is higher than A. Clock frequency of B is higher than A. Would it be a reason why A is fast? B uses a higher clock frequency. But A is fast. Not directly, yes, very good, Dalil. So that situation can happen, right? The situation can happen. The clock, A, B using a faster clock, A using a slower clock, but A still completes the work fast. That situation could theoretically happen, but the fast clock rate of B is not the reason, the direct reason why A is faster, right? So the situation could happen, yes, but the clock frequency of B being higher than A is not the reason that A is faster, but indirectly, it means if the hardware is complicated than A's hardware being complicated than slower, is the reason. So yeah, very good. So yeah, the clock rate of A is less than B. It's basically the same thing, right? Same thing as answer number 3, worded in a different way. Okay, good. So okay, now if some of you guys have other lectures or other work scheduled right now, just feel free to go. I'll continue to record the lecture and upload it in case. So I'll take a little bit more time to complete this section because we want to start the next topic next week. Okay. So instruction count and CPI. CPI is cycles per instruction. It's another definition that we used associated with computer performance. Cycles per instruction meaning is, as it says, the number of clock cycles that a computer needs to complete an instruction. Now, this is a somewhat confusing definition because instructions, individual instructions, there are different types of instructions, and these different types of instructions use different hardware in the data path. So the number of cycles taken per instruction as defined for a computer system overall is an average measure, right? So this number CPI defined for computer processor is an average which is dependent on the program as well as the instruction set architecture and the hardware, right? So it's a rough measure. It's an average that we define for a computer processor running a particular program. So also, you should understand something here. Now, if a processor, there are two types of processors when it comes to microarchitecture. You will learn it later, but I will give you a very brief overview. There are two types of microarchitectures when you implement an ISA in actual hardware. One is single cycle processors, the other is multi-cycle processors. See, in a single cycle processor, an instruction completes its entire execution within a single clock cycle. So an instruction is brought into the CPU, it's decoded, the register values are retrieved, the operations are performed, adding or multiplying or whatever, registers are updated, memory is updated, whatnot. So everything that you need to do for an instruction is done within a single clock cycle, right? Between two rising edges, everything is done in a single cycle processor. That is the definition of single cycle processor. In multi-cycle processors, this is different. The hardware is designed in such a way that an instruction will take multiple clock cycles, right? The decoding part will take a clock cycle. The reading of the register values will take another clock cycle. Then doing the actual operation like adding or multiplying or whatever, that will take another clock cycle, right? So an instruction will take multiple clock cycles per its operation, right, to complete its operation. So you should know that by this point. So cycles per instruction is defined as an average value because different instructions are going to take different number of clock cycles, especially on this multi-cycle CPUs. So then, okay, when it comes to CPU time, how is the CPI related to? CPI is related to the number of clock cycles. CPI times the number of instructions that you have in your program is the total number of clock cycles that program needs, right? On average, each instruction needs that many clock cycles. We have this many instructions in the program, so in total, we need that many clock cycles to complete the program. So with that definition, we can go back and update our CPU time definition as CPU time definition was clock cycles into clock cycle time. So we can say the number of instructions, CPI, clock cycle, all multiplied will give us CPU time. So if we use the clock rate instead of clock cycle time, we can rewrite it like this. So the instruction count for a program, the number of instructions, machine instructions that you will have in a program is going to be decided by the program itself, right? The algorithm itself, the program based on how you write your source code, as well as the instruction set architecture, which defines what are the available instructions that you can break this program down into, and also with the compiler. Compiler also plays a part in deciding how many instructions that you have in a program, because the compiler has to choose from the available instructions to come up with a composition for your high-level program. So the compiler can do an optimal job. It can sometimes not do an optimal job. So these are compilers again another program, right? So they can not always understand how to come up with the best possible solution. So they will try to do optimization based on how the compiler is designed, but it is also going to affect the number of instructions that you're going to end up with in your compiled program. So the average cycles per instruction, CPI, it's going to be an average. Always. That average number of cycles per instruction is going to be decided by the hardware, like I said, right? The hardware based on the design of the microarchitecture, how many clock cycles that a type of instruction is going to take, that is going to be decided. So based on how many cycles are being taken by different types of instructions in your ISA, your average CPI is going to be decided by that, right? So different instructions are going to have different CPI because different instructions are going to use different hardware elements in the actual microarchitecture. The number of clock cycles are going to be different for different instructions, different types of instructions. Then, yeah, so your program is going to have all these different types of instructions, right? All kinds of instructions like addition or loading from memory or performing floating point multiplication, right? All kinds of different instructions are going to be there in your program. The mix of instructions in the program is going to vary a lot. So that average CPI value is going to be affected by the mix of instructions in the CPU as well. That is why the compiler can affect the CPI value as well, right? All these things like compiler, IS, and everything is going to affect the CPI value, right? So let's try another example to use this performance equation that we came up with, CPI equation. So we have another two computers here, A and B, right? These two computers have different microarchitectures, but use the same ISA, same instruction set architecture, but different microarchitectures in the actual hardware. So computer A has a clock cycle time of 250 picoseconds and an effective or average CPI of 2 for some program, for a given program. And computer B has a clock cycle time of 500 picoseconds, right? 2 times as long as computer A, and an effective CPI of 1.2 for the same program, right? So we can assume, we can imagine that computer B has more complicated hardware, more complex hardware. That is why its cycle time is longer. But because some instructions may be completing in a lesser number of clock cycles for the same program here, the CPI is going to be less, right? The number of clock cycles consumed per instruction on average is going to be less for computer B. Okay, so for this program, which computer is faster and by how much? That is the question. Is A faster or is B faster by what factor compared to the other? Here is a summary of the same information. Computer A, cycle time 250 picoseconds, CPI 2. Computer B, cycle time 500 picoseconds, CPI is 1.2. Uses the same ISA, runs the same program. These CPIs are designed, given based on a certain program. And which computer is faster? By how much? Can anyone answer? Rhythm says B is faster by 0.8%. Chatura says B is faster 1.2 times than A. Let's have a look at it. So CPU time for A based on our equation, instruction count, CPI, and cycle time. So instruction count we don't know, we define it as I, okay, some number of instructions. And CPI for A is 2.4 and cycle time is 250 picoseconds. So I times 500 picoseconds is the CPU time for A. For B, the same thing boils down to the same number of instructions, right? Same program, I, and CPI is 1.2, cycle time is 500 picoseconds, so I times 600. So CPU time for B over CPU time for A is 1.2. So which one is faster? A, right? CPU time for A is the smaller one, so A is faster by that much, right? A is faster. A has the lower CPU time compared to B. A is faster by this much. Okay. So I hope the working of the concept here. So this combines all our equations that we have used so far, right? The equations for CPU time and the equations for relative performance. Not these things are not complicated, very simple stuff, right? You can even work this out on your own common sense, using your common sense. Right. Okay. So I told that different types of instructions are going to consume different numbers of clock cycles inside the CPU. So based on that, we can define classes of instructions, categories of instructions. For example, say instructions like add, sub, and maybe even instructions like logical or logical and things like that can take the same number of clock cycles inside the CPU because they are using a very similar section of the data path, the functional units that these instructions used inside the computer are same or very similar. So based on that, you can define classes of instructions, right? One class of instructions would be these arithmetic and logic instructions, which are going to use very similar very similar hardware functional units in the CPU. But say you can define a different class of memory, different class of instructions for memory related things, right? Loading from the memory, loading a word from the memory, loading a byte from the memory, or storing a byte into, storing a word into the memory. So those types of instructions can be a different class because they are going to use a very quite different functional units compared to the other arithmetic or logic instructions that we talked about. So based on that condition, based on that information, we can define these classes of instructions, and those classes of instruction would have their common CPI values, right? So say if we could have say n different instruction classes, and from each class of instruction we could have a number of instructions in the program, and for that class we define CPI because CPI is common for that class. So we can come up with the total clock cycles for the program like this, right? So you can multiply the number of instructions of a similar class, the same class, with that class of CPI, and we can keep adding terms like that for all the classes of instructions that we have in the system. So we can come up with clock cycle times, the total number of clock cycles like that, with a weighted average CPI. at the end of the day, right? So the weight that we use is CPI for each class or each category of instruction. Yeah. Weighted average of CPI, the total overall CPI value we can define like a weighted average, but as what you see in this last equation here, right? CPI is basically number of clock cycles divided by how many instructions we have there, because CPI is an average value, and that can be written using the previous definition here based on the different classes of instructions. Okay. So the take-home point is CPI can be, we usually define it as an average and as an overall value for the entire system based on the program, ISA and everything. But it can be broken down into CPIs for different classes of instructions, because those the instructions in a single class will have a lot in common based on the hardware that those instructions are going to use. Right? So this term here can be defined as relative frequency. How many instructions of a particular class that you have in your entire program, the fraction compared to the total instructions in the program is the relative frequency. Some very simple stuff. Okay, another example to sort of understand this better. We have the same program, but the program is compiled in different ways by a compiler, right? We have alternative compilations of the same code using these different classes of instructions, right? So in our instruction set, we have 3 different classes of instructions. A, B, and C are the classes of instruction. So for an instruction in class A, CPI for that class is 1. It's going to take 1 cycle on average. Then for instructions in class B, they are going to take 2 cycles. Instructions in class C are going to take 3 cycles, right? And we have 2 different assembly sequences given by compiler, given by our compiler. Compiler may be optimized for different purposes, right? The same program, the compiler optimized for one purpose will give sequence 1, optimized for a different purpose will give sequence 2. So in the sequence 1, in the assembly sequence 1, we have 2 instructions from class A, 1 instruction from class B, and 2 instructions from class C. In second assembly program, we have 4 instructions from class A and 1 each from classes B and C. Right? This is the same high-level program compiled into 2 different assembly sequences. So in sequence 1, we have a total of 5 instructions, right? 2 plus 1 plus 2, a total of 5 instructions. And the clock cycles the program is going to take is what? 2 times 1, 1 times 2, 2 times 3, right? Total 10 clock cycles, right? We have 2 instructions from class C. Each of them are going to take 3 clock cycles, so 6 clock cycles for those 2 instructions. Likewise, you can add the number of clock cycles taken for the entire sequence of 5 instructions and come up with the answer 10 clock cycles. So the average CPI for that sequence on that computer is going to be 10 clock cycles divided by 5 instructions, 2. The alternate assembly sequence number 2, we have 6 instructions total, right? 4 plus 1 plus 1, 6 instructions total. We have more instructions, but the majority of those instructions are from class A, which is a faster class of instructions. So the CPI is less for that class. So we have 4 times 1, 1 times 2, and 1 times 3 clock cycles total. So here, total number of clock cycles is 9, which is a single clock cycle less than the sequence 1. So average CPI for the sequence 2 becomes total 9 clock cycles divided by 6 instructions, 1.5. Right? So I hope this gives you an insight into what the meaning of this average CPI and CPI defined for classes of instructions. Okay. Now we come to the summary of our big picture, right, of performance. So CPU time, based on all the definitions that we went through today, the total number of instructions in the program into the total number of clock cycles taken by each of these instructions into the time taken per clock cycle, right? So cycle time. This is cycle time, this is CPI, and this is instruction count. So performance depends on algorithm at the algorithm level, right? Performance depends on what you have at the algorithm level. Because at the algorithm level, you define the time complexity, which is like the number of operations that you need to perform, and that is going to affect the instruction count, the number of instructions in your assembly program, and that is indirectly going to affect the CPI, average CPI as well, because the number of instructions in your program is going to affect the average CPI. So then the programming language, it is going to affect the instruction count, right? The programming language defines what sort of operations you can do in your source code, what are the operations that you can write. And based on that, the instruction count in the program is going to be decided, right? It's going to affect the instruction count. And again, the CPI, because the instruction count is going to change. Then the compiler is going to affect the instruction count. Compiler can optimize your assembly program for different purposes, right? Based on how the compiler is designed. So it's going to affect the instruction count and in turn, indirectly, the CPI as well. Instruction set architecture is going to affect the instruction count, obviously, right? Because instruction set architecture decides what are the available instructions. So to do a certain operation, how many instructions you need is going to be decided by that. So instruction count is going to be affected by the ISA. CPI is going to be affected by the ISA because the instruction count is going to be affected, as well as the nature of the instructions is also going to affect the CPI directly. Then it is also going to affect, ISA is also going to affect the cycle time as well, right? Because the hardware is designed based on the ISA. So the cycle time of the clock is going to be affected by that. So the ISA is going to affect all of it. So the performance is going to be dependent on your algorithm, the programming language you use, and source code that you write, the compiler that you use, and what sort of optimization the compiler will be performing, and then the ISA that is used here in this particular in your particular system, and the hardware that is being based on this ISA, right? So all of these things are going to affect the performance at the end of the day, and you can break down the performance into the using a response time measure, measuring it as CPU time, based on the equation that we have been twisting and turning in different ways. It's the same equation that we used, right? Okay. These exercises we will not go to discuss in the class, but I'll upload this slide so you can go through. These are very simple exercises that you can use to understand these concepts better, right? These are the same things that we have discussed in class so far today. And Yeah, we'll not go into those details. Right. The last thing that we are going to talk about today is something called Amdahl's law. This law says improving an aspect of a computer and expecting a proportional improvement in overall performance is a pitfall in designing computers, right? So you're going to, if you're improving one aspect of a computer and expecting a proportional improvement in overall performance, is not going to work. It's a pitfall. You can't expect that to happen like that, right? Because for one reason, only the affected components are going to be improved by the same factor that you're going to use for this improvement. Say doubling the clock rate or doubling the number of functions, yeah, whatever the factor that is a part of the improvement that you're talking about. Only the affected thing, directly affected components are going to improve proportionally. There are going to be components that are unaffected as well. Like some components in your CPU will not be affected by the improvement that you're going to do. So you can't expect a proportional improvement in overall performance. Also, like we discussed earlier, improving a certain factor for performance also might negatively affect some other aspects of performance, right? Like the number of clock cycles versus the cycle time, what we discussed earlier, right? So like that, improvement in one factor can also negatively affect another component in the system. So for all these reasons, improving one aspect and expecting a proportional improvement in overall performance is not going to work. So, yeah. So in this example, we have a program which takes 100 seconds. Out of that 100 seconds, 80 seconds are taken by multiplication operations, right? So how much improvement in multiply performance do we need to do in order to get 5 times overall performance? Right, so overall, the program is taking 100 seconds. Out of that 100 seconds, 80 seconds are taken by multiply operations. Now, we are going to improve the performance by improving the performance of the multiply hardware. So, if we want to get 5 times overall performance, how much should we improve the performance of multiplication operations? How much of a performance improvement should we expect for multiply operations? So overall 5 times performance, meaning the program that runs in 100 seconds, we should be able to finish in 20 seconds. Right? Can we do that? By only improving the performance of multiplication operation, can we do that? No. Right? Then we need to get rid of the time that's taken by multiplication entirely, and leave the rest of it, the remaining 20 seconds as it is, and end up with 20 seconds overall time. And that can't be done, right? Because multiplication is part of this program. So that is what this pitfall is all about. So the idea is, yeah, we need to make the common case faster, right? That is the design principle that you will be seeing in the tutorials as well. Yes, we need to make the common case faster. If there is a common element which is going to consume a lot of time because it is being repeatedly used, trying to make it faster is what we do, but we can't expect a proportional improvement in overall performance because only a certain part of the hardware is going to be affected by what we are trying to improve. Right. Okay, so concluding remarks for chapter 1. As we saw from the first lecture, we talked about how technology evolved and what were the underlying concepts that helped us improve technology and in turn improve performance. So the cost of a computer system and performance of a computer system has been improving and it is still improving due to underlying technology developments, right? Different developments in technology. We saw how certain challenges were faced by certain ways we tried to improve technology and how we solved it, right? How we came up with different solutions like multiprocessors when we couldn't improve, keep improving the clock rate. Yeah, so things like that. So then we talked about hierarchical layers of abstraction that we have in a computer system. And these layers of abstractions are present in both hardware and software parts of computer systems. And they are interacting, right? They're connected to each other, the software abstractions as well as hardware abstractions. And then we also talked about what are the things that we are going to cover in this course, what are things that abstractions that you have covered in previous courses, and the things that you are going to cover in upcoming courses in your computer engineering program. Then we talked about instruction set architecture, how instruction set architecture is very much key to the to bridge the hardware and software sides of a computer system, right? How the instruction set is acting as the interface between the hardware and software system. And we will also, in the next chapter, you will learn a lot more in detail about instruction set architecture. Then we talked about performance and mainly execution and response time. And execution time is the best performance measure when we want to talk about designing computer systems for a particular purpose, right? Execution time or response time is the best measure of performance for us as engineers who are going to design computer systems. Then power is a limiting factor. We saw it related to the technology improvements as well. Power is a limiting factor that was a big challenge that the development in computer technology had faced. And how it was overcome is using parallelism, exploiting parallelism in the programs that we write to improve overall performance. And that is also something that we will be covering in the rest of this course. Okay, so that's it for this chapter, and I'll stop recording.